All right, good evening again, and welcome to the HamSCI Workshop Banquet, the 5th annual HamSCI Workshop. I'm very pleased to present this evening's banquet keynote speaker, Dr. Chen-Pang Yeang. Dr. Chen-Pang Yeang is an associate professor at the Institute for the History and Philosophy of Science and Technology at the University of Toronto. Trained in both electrical engineering and the history of science and technology, he does research and teaching in the history of physics, electrical engineering, information and computer science, and technology in the 20th and 21st centuries. He published Probing the Sky with the Radio Waves, from wireless technology to the development of atmospheric science. He is completing a book on the history of noise, which I know will actually be of interest to many people in this room. In addition, he is undertaking a research project that uses the material replication of Heinrich Hertz's radio wave experiment as a means of historical inquiry, and another project on the grassroots innovation of information and computing technology. With that, I'd like to actually first, Christina, would you like to say anything to? You're good? Okay. So thank you. So with that, I'd like to introduce Dr. Chen-Pang Yeang.
Good evening, everyone. Thank you very much, Nathaniel, for the warm introduction. And it is my great pleasure to give a plenary talk at the HamSCI 2022. And I would like to express my gratitude to Professor Nathaniel Frisso for inviting me to give this talk. I'm sorry for not being able to come to the meeting in person, but I'm still very enthusiastic of what I'm going to talk about and share with you in this talk. So as Professor Frisso mentioned, I am a historian of science and technology. So I'm not a ham radio operator. I don't own or operate a ham radio station, but I do study the historical past of the ham radio communities and their technical works and their sort of community interactions. So that is what I'm going to talk about today. So today I'm going to talk about ham radio and the discovery of the ionosphere. So from the historical point of view, the stories of radio amateurs is especially interesting because it shows us sort of alternative path of developments for science and technology in the modern times in the 20th and 21st century. So the mainstream science and technology in 20th and 20th century has been highly professionalized and specialized. But what the radio amateurs community opened up were the sort of alternative development path in which the more community involved and grassroots activities became more and more possible. So in the realms of technology, we know from extensive historical study that ham radio was an exemplar of what I can call the grassroots technological innovation. So for example, historian Susan Douglas pointed out the close connection between the inventions of radio broadcasting in the 1920s and the radio amateurs' involvement in that invention. And also some historians of computing found the important roles of the ham radio communities and radio amateur magazines and their activities in the inventions of the personal computers in the 1970s. So in the realms of science, of course, this very conference, this very workshop, HamSCI, is sort of a reflections of the ham radio community's close involvements of scientific research. So maybe we can say without exaggeration that ham radio exhibited a sort of model and pioneering roles of the citizen science as we now call today. And that's that sort of community level and distributed style involvements of scientific research and data collection actually has been going on for quite a while, dating back to the early 20th century. So actually, historically, we cannot avoid pointing out the close relationship between the ham radio communities and the studies of the planetary science. So that is exactly what I'm going to talk about today. The radio amateurs and the discovery of the ionosphere. So while we look into this story, I think it's worth keeping two issues in mind, two broad issues in mind. And one is that how this story can give us an opportunity to rethink the meaning of experimentation. So the ham radio's community's involvement with the discovery of ionosphere was embodied in a series of experiments. But these experiments were organized and done in a way that were fairly different from the sort of laboratory science or the kinds of field experiments done by professional scientists or engineers in the companies and governments or academic institutions. So knowing that, we can further ask, how did the citizen science, like what the ham radio community did in the early 20th century, complement the professional science? So in what sense did their highly distributed and community level and sort of flexible style of experimentation and mass participation, large-scale trial, how did that give us some lessons about the importance of this new kinds of or this kinds of experimental pursuit, which I believe is a sort of very nice complements and perhaps we can say corrective to the probably over-specialized and over-professionalized science and technology at modern times. So in order to understand that story, we have to know a little bit backgrounds about the beginning of wireless technology and radio propagation studies in the early 20th century. So it is well known that the wireless technology, the radio technology can trace back to the German physicist Heinrich Hertz's discovery of electric waves in 1887. So this is a replications of Hertz's instrument, so-called spark gap generator, and the loop detector that he used to identify the phenomenon of electric wave, which is the radio bandwidth electromagnetic wave. And I want to show you this photo because this is a sort of replication set that my research team and I constructed in Toronto. So after Hertz's discovery, in the following decades, a number of inventors managed to turn the electric wave into the technology of wireless telegraphy. And these entrepreneurs included the British-Italian Guglielmo Marconi. So their innovation involved the introductions of new devices for the signal transmissions and receptions and antennas and the sort of hardware infrastructure for wireless telegraphic communications. So by the very end of the 19th century, people like Marconi established the wireless telegraphy and the information infrastructure for the range of communication within like dozens, tens, or at most 100 miles of distance. But then in 1901, Marconi undertook an ambitious experiment. So he took a research team. So he took a an engineering team with him and brought a telegraphic receiver to St. John's, Newfoundland, and then he he tried to receive the signals transmitted from his Marconi wireless transmitting station in Podu, England. And in December 1901, Marconi claimed success for receiving this transatlantic wireless signal. So this, of course, became an immediate sensation in mass media at the time. And it also opened up the possibility for long-range wireless communication. But this experiment also raised an interesting scientific question, which is, why can radio waves propagate over such a long distance without being blocked by the curvature of the Earth? So in the following 2 decades, scientists and engineers tried to came up with 2 theories to explain this phenomenon of long-distance radio wave propagation. Well, the first theory was the so-called surface diffraction theory. It was first entertained by the Cambridge mathematician Hector Monroe McDonald in 1903. So basically, this theory modeled the idea that radio waves propagate over long distance because they diffract along the Earth the curvature of the Earth's surface. So this is basically a diffraction phenomenon. Well, in the following 2 decades, a number of prestigious and prominent mathematical physicists and mathematicians endeavors to develop further this surface diffraction theory. And they included the Munich-based physicist Arnold Sommerfeld, Auguste Love at Oxford University, and Henri Poincaré in Paris. So basically, this surface diffraction theory was highly mathematical. It involved the formulations of the problem as a wave equation plus the boundary condition, which is the radiation dipole as the transmitting antenna sitting on top of a conducting Earth surface as a sphere, conducting sphere. And then these mathematicians and theoretical physicists tried to obtain the analytical solution of this equation under the boundary condition as a sum of sort of basis functions, and further made some further approximation to reduce them in the simple form. So briefly, this was the mathematical tour de force, and it involved highly complicated mathematical exercise. But on the other hand, in 1902, 2 other individuals were involved in producing or proposing another possible model for long-distance radio wave propagation, and they were Oliver Heaviside in London and Arthur Keneally, professor at Harvard University in Boston. So in the atmospheric reflection model, it was assumed that the radio waves could propagate over long distance along the Earth because they were bouncing back and forth between the Earth as a conductor and an upper layer, which is another conducting layer in the upper atmosphere and is concentric to the surface of the Earth. So this atmospheric reflection theory to Heaviside and Keneally was basically a qualitative theory. It was a physical model, but it did not involve the kind of sophisticated mathematical apparatus that the surface diffraction theorists developed. So this was the status of the theoretical explanation for the long distance wave propagation. But at this time, when the 2 theories were proposed, there was no adequate and reliable quantitative empirical data to compare with. That situation began to change in 1910 to 13 when an American physicist, Louis Austin, working for the US Navy, launched a sequence of experiments. So Austin's experiment involved putting a radio telegraph receiver on the battleship, and the battleship set sail to the Atlantic Ocean and tried to detect the signals transmitted from the wireless U.S. Navy's wireless stations on shore. So while the battleship moved across the ocean, it has further and further distance away from the transmitting stations, and therefore it could record the signal intensity as a function of distance. So that was exactly what Austin and his assistant Cohen did. So in 1913, Austin and his team synthesized the empirical information, empirical data into an empirical formula, which was known as the so-called Austin-Cohen formula. So in this formula, you can see that the received signal intensity decays exponentially with distance, with the coefficients proportional to the inverse of the square root of the radio wavelength. So this is this was a sort of well accepted empirical formula for radio wave propagation. But at this time, the atmospheric reflection theory could not produce any quantitative prediction to compare with this empirical formula, whereas the surface diffraction theory, even though it could produce some prediction formula to compare with the Austin-Cohen formula, the results actually were discrepant to each other. So specifically, the surface diffraction theory predicted more severe decay with distance than the Austin-Cohen formula. So at this point, there was a significant mismatch between theory and experiment. That situation changed again in 1918 and 19, when another Cambridge-trained mathematician, George Neville Watson, came out to do some further synthetic mathematical work. So basically what Watson did was to treat the atmospheric reflection theory as another set of boundary conditions. And here you have this, you have the Earth as a conductor and the upper conducting layer and the free space in between. So that's another more complicated boundary condition. And then he managed to solve the wave equation with this new boundary condition of atmospheric reflection. And then he found a mathematically consistent approximation for the resultant solutions. And that result, that approximation, could be reduced to a simple form formula, which was consistent with the Austin-Cohen formula. So here is a very nice story that closed the loop between theory and experiment. And at this point, the theoretical prediction matched nicely with the empirical formula of the Austin-Cohen. So an important implications of the Austin-Cohen formula and the vindication by Watson theory was that according to the formula, the longer the wavelength, the longer the propagation distance, because the radio waves decays more slowly with increasing wavelengths. So the implication was that if engineers and governments wanted to design a radio transmitting station for long distance signal communication, then they had to go for long wavelengths, right? And as a result, companies and governments around 1910s and 1920s all enacted the long wave stations with wavelengths longer than 200 meters and perhaps even longer. So this low frequency radio wave stations or the transmitting stations require very high antennas. And so they have gigantic antenna towers. On the other hand, governments and engineering and scientific communities believe that the short waves were sort of less useful, especially for long distance communication. So they gave those parts of the radio bandwidth to amateurs, to the ham community. So that set the stage for the amateurs' involvements in the radio wave transmission propagation experiment. But before go on to that story, we'll mention one more piece of the theoretical work, which is the so-called atmospheric refraction theory, ionic refraction theory. So when the physicists and engineers and mathematicians were developing the surface diffraction theory and atmospheric refraction theory, there was another theory being entertained in the 1910s. And that theory actually moved the focus from the boundary condition, like conducting surface, like metallic-like surface in the upper atmosphere, to account for radio wave propagation, to another set of physical scenario, which involve not a single boundary, but a geophysical region in the upper atmosphere. And that region had a structure. It's not just a single flat, not flat, it's a sort of single boundary. And so that represents a conceptual shift from the atmospheric reflection to ionic refraction. So in these new versions of the theory, what existed in the upper atmosphere was not a sheath of conductor like a metal sheets, but rather regions of layers and layers with different densities of charged particles. So with this theory, the focus or the major explanation for long distance radio wave propagation was no longer bouncing back between the Earth and the upper conducting layer, but rather to trace the bending of the radio waves in the upper regions of the geophysical characteristics with certain geophysical characteristics. So this is a significant conceptual shift. And this ionic refraction theory was first entertained by a British engineer, William Henry Eccles, in 1912. And then it was further developed by a prestigious Cambridge physicist, Joseph Larmor, in 1924. So Eccles and Larmor's theory basically was that the radio waves actually were refracted in the upper atmospheric layer. And this upper layer actually comprises a large body of ionized airs, right? And because the ionized air had different density at different height, so as a result, we can anticipate that the refractive index, which is determined by the ion density, decreases over height. So because of this refractive index profile, we can see the bending of the radio waves downwards due to the profiles of the refractive index. So that was the essence of the ionic refraction theory. But this theory looks fascinating, and it's closer to what we know today. But then back to the 1920s and the 1910s and 20s, we should ask, where was the evidence for this kind of theory? And that's where the ham radio community and their collective experiment came to the story. So radio amateurs appeared as early as the beginning of the 20th century, when the wireless telegraphic technology became commercialized at the time. So initially, the radio amateurs were sort of an individualized activity. So those were the activities of the young, usually young, enthusiastic wireless telegraphic operators who wanted to build up their own stations for receiving or even transmitting wireless signals. But then, but quickly after the first decades of the 20th century, we witnessed the growth of the formations and growth of wireless amateur clubs around the Western world, especially in the United States. So it was estimated that by the early 1910s, there probably hundreds of wireless radio amateur clubs around the United States. So in 1914, the radio amateur community had important developments. The inventor, entrepreneur, and also ham radio operator, Hiram Percy Maxim, organized or created an organization called the American Radio Relay League, which I believe everyone in this room knows, right? So that American ARRL was established at Maxim's hometown, Hartford, in Connecticut in 1914. So ARRL had an ambitious aim of organizing and making alliance, connecting the wireless, ham radio clubs around the country of the United States. And it was at this time, after the establishment of ARRL, that we witnessed the increasing interest of ham radio operators to experimentation. So there are a number of political, institutional, and technical and social factors contributing to that increasing interest among the ham radio community to do experiments. So one important factor was the political factor. So in 1912, US Congress passed a law which is well known as the Radio Act of 1912, and that law restricted the use of wireless amateur access to wavelengths only shorter than 200 meters, right? So the reason was just I explained. At this time, the engineers and scientific communities strongly believed that the short waves were useless for long distance communication based on their empirical and theoretical studies. And of course, this was the time when the American governments were trying to regulate and to restrict the spectrum access of hobbyists of ham radios, and organizations like IRL tried to fight back, to fight for their freedom and their access to the spectrum right. And they found, or they tried to establish that that experimentation or their possible potential contribution to science could be an important way to legitimize their lobbying for the amateur right to spectrum. So that was the important political background for the amateur switch to experimentation. And now, on the other hand, the 1910s was a time when the wireless technology, radio technology was fast developed. So a lot of the ham radio operators during World War I were recruited into the armed forces, and they had the firsthand experiences with the cutting edge new radio technologies while they're doing their military service as radio operators for the Navy or the Army. And so the new technologies they experienced, they had firsthand experience or even participate in developing, included things like the feedback amplifiers, the electronic tube circuits, the super heterodyne receiver, and the tuning circuits, and the wave antennas. So these were all like pages extracted from wireless from the ham radio magazines, which shows that they were very well aware of this cutting edge technological development in wireless technology. And on the other side of the Atlantic Ocean, there were comparable radio amateur organizations in the UK and France. But in the case of Europe, the laws actually had even more strict regulations about amateurs' right to the spectrum. And the law stipulated that the major purpose or the major desiderata for the organization, for the very existence of ham radio, was to do scientific experiments, right? So that was part of the law. So for the radio amateur organizations like the Radio Society of Great Britain in the UK and Société des Amis de TSF in France, they had even stronger motivation to participate in or even develop their own scientific experiment. So the first scientific experiment, large-scale scientific experiment that the ham radio community tried to undertake was the so-called fading experiment. So fading referred to the irregular intensities of received radio signals over time, right? So as early as the 1900s, wireless telegraph operators already noticed the phenomenon of fading. So through the decades of experience with the operations of radio telegraphy, engineers and technology found that the fading was a tricky phenomenon, right? So this irregular array variation actually changed with a lot of different conditions, like the geographic regions, like different seasons or different times of the day. So this geographical, seasonal, and diurnal contingencies make it difficult to sort of reduce the phenomenon of fading with simple like mathematical or physical regularities, mathematical formulas or simple physical explanations or simple ways of representing the phenomenon. So because of the because of the natures of this phenomenon, actually a huge amounts of data that cover different like local heterogeneity, different local variations were the better way to represent the phenomenon and to represent the data. So because of this nature, the very problems of the fading actually call for the kind of citizen science as we know today, to get as much data over as much variation, as much diverse conditions as possible. So the first idea for bringing the radio amateur communities for experimental investigations of fading came around 1920. So in April 1920s, John Howard Dallinger at the National Bureau of Standards organized a meeting with a number of professional engineers and ham radio operators in Washington, D.C. So the participants of this meeting included the Maxim of ARL and his assistants his assistants and important figures of the ARL, Kenneth Warner, and also Albert Hoyt Taylor, a researcher and naval officer at the U.S. Naval Research Laboratory in Washington, D.C. So what came out of this meeting was the decision to undertake a coordinated mass experiment. And under their plane, a number of trials would take place from June 1920 to April 1921. So basically that duration covered the whole seasons, right? And the geographic regions that were involved in this fading experiments included New England, New York, Virginia, Illinois, Indiana, and Ohio. And 17 ham radio transmitting stations were involved in the fading experiment. Their operating wavelengths range from 200 meters to 375 meters. And 150 receiving ham radio stations were involved in receiving the signals, right? So of course, this was the scale of this experiment was large. So in order to achieve that scales of participation, ARL actually called for the general participation in the postings published in their flagship magazine QST, right? And also they published the schedule of the experiments well in advance. So the well, one issues about this mass participated experiment was that they could not control, the organizers, ARL and National Bureau of Standards, could not control sort of the qualities of each participants, right? So these amateur stations came from all different backgrounds. So in order to ensure some kind of quality maintenance, quality control, the ARL and National Bureau of Standards actually were trying to standardize the procedure, the experimental protocol and procedure and data formats. So this is an example of the standard experimental report that the ARL design. So as you can see in this report, each participants of the experiments required to fill like typical information like the station number, the locations, and the transmitting power, etc. But also they were required to record the received signal strength in the table that they provide, that the ARL provided. So this horizontal axis represent the time and vertical represent the signal intensity. So they degrade the signal intensity into several levels and ask each ham radio operator to recognize, like at each time instance, what was exactly the signal intensity they could recognize, right? So that was not a trivial matter because a lot of these ham radio operators were very good at recognizing the message, the contents of message, but they were not so good at recognizing the signal intensity. So ARL had to do some work teaching or educating the ham radio operators that to direct their focus to that instead of this. So the results of the fading ARL and NBS fading trials generated thousands of records. And the National Bureau of Standards were trying to analyze this, to undertake some statistical analysis of the data. But the result didn't seem to provide any substantial scientific conclusion out of this massive data. So rather, the more significant part of the NBS ARL experiment was the process, because the campaign laid out a model for ham radio's mass experiment. So it laid out a way for the mass participations of the radio amateur communities to join a pre-scheduled experiment. So that was the model that the ham radio community went for when they were trying to conduct the long-distance radio wave transmission experiment across the Atlantic Ocean. So that idea first came out around the time when they were doing the fading test in 1920 and 21. And as I just mentioned, at this time, professional engineers and scientists did not have too much confidence in the possibility of transmitting radio signals across long distances at short wavelengths, shorter than 200 meters. And that was exactly the wavelengths that the radio amateurs were assigned to use. But the radio amateurs were not deterred by this sort of pessimism from professional scientists and engineers. Rather, they were quite enthusiastic about the idea. So in 1920s, ARL and the Wireless Society of London were talking about organizing this large-scale transatlantic trial for signal transmission. So according to their plan, 3 nights were scheduled for the signal transmission, the 1st, 3rd, and 5th of February 1921. So these experiments involve 24 American stations for transmitting signals. On the other side of the Atlantic, there are 250 British amateur stations for receiving the signal from the 24 American transmitting stations. So the experiment was conducted. Unfortunately, no evidence appeared for showing the success of transatlantic signal transmissions. So after the experiments, ARL and Wireless Society of London had discussions about the possible causes for the failure. Well, the causes, they they did not believe that the cause was because science prohibited this from happening, but rather these were causes that they believed could be remedied. Well, one was that there too few nights were assigned for the experiment. Maybe they should expand the days or nights for the trial. And also they found that there was significant interference from the commercial stations, and also interference from the feedback circuits of the amateur stations. And finally, especially the American amateurs found that maybe perhaps the British amateurs receiving skills and techniques were not adequate enough, were not good enough for this kind of trial. So that had to be improved too. So right after the first transatlantic trial, the wireless ham radio communities across the Atlantic Ocean organized the second trial. So this time they planned for nights instead of the 3 nights from 8 to 17 December 1921. So like the previous one, the stations in North America, the American and Canadian stations were responsible for transmission, whereas the European stations were responsible for receiving the signals. And again, just like the fading experiments, in order to mobilize the mass participation, ARL posted the request for participation in QST in September, just like this one. And to respond to this request, there were 78 transmitting American stations volunteered to participate, but they got together to undertake a preliminary trials in early November 1921. So after the preliminary trial, 27 transmitting stations were selected. So these were more high power stations that produce more higher quality transmitted radio signals. And another measure that the amateur communities took to ensure the quality of the experiments and ensure to increase the chance of success was this design of a 2-tier participation. So according to their plan, every night of the experiment was divided into 2 parts. From 7 to 9:30 p.m. EST, the time was open, the air was opened up for all North American stations to transmit signals to Europe. But from 9:30 p.m. to 1 a.m., only this 28 pre-selected transmitting stations were allowed to transmit the signals. So the purpose of this 2-tier participation was to mobilize mass attendance on the one hand to increase the chance of success, but on the other hand, to have better quality control parts of the experiments on the second part of the night. So, and another measure that the amateur community took was to send some dedicated experimenters to do the experiments in addition to the mass participation. So the ARL selected this guy, Paul Godley, who had experience with military telegraphy and commercial telegraphy, but also was an avid ham radio operator. So Godley was sent by ARL to the UK, and he brought with him a cutting-edge super heterodyne radio receiver to do the job. So the idea is that he would set up a receiving station in Ardrossan in Scotland, so that because his receiving skills and equipment was better trusted, so that would give a better chance for the radio for the receiving of the signals. And finally, this kind of experiment was not like the typical scientific experiment, because the purpose was not to come up with quantitative precision, quantitative data with precision, right? So the quantitative precision was not an issue. Rather, the goal was to successfully transmit the signals across the Atlantic Ocean. So the credibility of communication was a real issue underlying the experiment. And in order to establish credibility of data, actually each of the 28 stations were given in advance secret cipher combinations for the signals they're supposed to transmit, right? And then all the supposedly in principle, none of the British radio ham operating stations were should know these combinations. Only one organizer, American organizer, knew this combination, and he was sent to the UK and was supposed to supervise and review all this the claimed receptions of signals. So that was one way to ensure the credibility of signal reception. And also this guy, Paul Godley, was under the continual and close supervision and surveillance to make sure that he did not cheat. So the results, after these measures, the result turned out to be quite successful, right? So this was the announcement, excited announcements in QST to report the success of the second transatlantic trial in late 1921. And this is the sort of summary of the results of the second transatlantic trial. So Godley himself received signals from 28 American and Canadian transmitting stations. And in addition, there are 8 British receiving stations received signals from 11 North American transmitting stations. In addition to that, there are also stations in Nice, France, and The Hague, the Netherlands, which received the North American signals. So right after the, well, this, of course, this was great news for the radio amateur communities across the Atlantic Ocean. And immediately after that, they launched the design for the third transatlantic trial. And for this trial, not only the radio communities in the UK and the US were involved, but also in France. So the organizer for the transatlantic, the third trial, involved the ARL, Radio Society of Great Britain, and a committee composed of numerous French amateur radio societies. And in this round, in this new trial, the third trial, both the eastwards and westward communications were plain. So in other words, not only American stations transmitted signals to Europe, but also European stations were supposed to transmit signals to America. And like the previous trials, they call for mass participation in ham magazines. And another measure that the British amateur radio community tried to undertake was to build a dedicated station exactly for this purpose. So the Radio Society of Great Britain built this station 1KW, built station 4WS in London. Then this station had a high power of 1 kilowatts. And at that time, the British amateur station were only allowed to have up to 10 watts. But this had the sort of 2 numerical orders above, exactly for that purpose. And the schedule went as following. The American and Canadian transmissions supposed to happen in from 12 to 21 December 1922, and the British-French transmission supposed to happen on 22nd to 31st December 1922. So here are the results of the third trial. And as you can see, in this two-way experiments, the American transmission and European reception was much more successful. So the British hams received 161 North American transmissions, and the French and Swiss hams received even more American transmitting station signals. But only 2 European transmitting stations reached North America. The 5WS in London and another station 8AB in Nice, and that French one was operated by Léon Deloy. So before the third transatlantic trial, Deloy already undertook a very interesting so-called two-way trial with a number of American ham radio operators in Hartford. So in November 1922, the Lost 8AB actually successfully communicated with the Freshnel and Warners and John Rhinas in Hartford. And the next day, they actually achieved the two-way communication. In other words, the lost French stations could transmit signals to the Hartford station, and the Hartford stations could also transmit signals successfully to the station in Nice. So inspired by this, the fourth transatlantic trial were planned for December, from the late December of 1923 to the early January of 1924. And this time, the European stations were responsible for transmission, and North American stations were responsible for receiving. And well before the experiments, ARL urged American ham radios to keep radio silence during the period of time. So this actually worked, right? So as a result of the fourth trial, 42 European stations were heard. So now it was demonstrated that this signal transmission across the Atlantic was not just one way. It could go one way or the other. So the ham radio operators' transatlantic trials show the plausibility of long distance propagation for wavelengths shorter than 200 meters. And this, of course, was a contradiction to the Austin-Cohen formula and the Watson's theory. So it defined scientific predictions. But it was successful. So the results of the ham radio operator shows the need to probe further into the atmospheric layer in order to modify the well-received scientific theory of atmospheric refraction. So this was a turning point toward the increasing acceptance of the ionic refraction theory. And finally, the way of the radio amateurs' wave of doing experiment involved collective mass participation, and that involved distinct forms of mobilizing participation, designing operational protocols, and establishing credibility. So all these were special features that we did not usually see in the experiment managed by the scientific laboratories or engineering companies or the military or government organizations. So I don't think I have time to go over the sort of discoveries after the radio amateurs transatlantic experiment, but let me just say it quickly. After the radio amateurs transatlantic experiments, a number of professional engineers collaborated with the radio amateur communities to probe further into the shortwave propagation. So they discovered a very important phenomenon called the skip distance, and also the sort of non-monotonic change of the range, signal transmitting range with frequency. So the discoverers of this phenomenon included John Rhinas of the ARL and Albert Hoyt Taylor at the US Navy. So Taylor even developed a theory to explain the skip distance as a result of sort of ion density profile. And the reason why the radio waves skip was because at large angles, the ionized region did not have sufficient refractive power to bring the radio rays downwards. So instead, the radio rays escaped to the upper sky. So that was sort of a very important piece of work toward the sort of the establishment of the reality of ionosphere. And also in the mid-1920s, two set of experimenters designed experiment to verify the existence of the upper ionosphere, and they were Edward Appleton at Cavendish Laboratories and Gregory Bright and Merle Tooth at the Carnegie Institutions of Washington. So in both experiments, a radio transmitter and receiver were used, but it was detected that the receiver actually could receive two sets of signals, one from directly from the transmitter, and the other going through the upper sky and bending downward. So by sort of figuring out the interference relationship between these two rays, these two waves, they could infer the height of the upper layer and therefore establish the reality of the upper ionosphere. So after this experimental work, eventually radio scientists and atmospheric scientists established the reality of the ionosphere. And all this reality of ionosphere was based on the radio experiment. So that's why we can call it the radio ontology of the ionosphere. So let me give a very brief conclusions of the story. So in the story, as we can see, ham radio played a crucial part in the discovery of the ionosphere. And they could do so because they thought and acted outside the box of the professional scientists and engineers. In other words, the ham radio operators believe that the professional scientists and engineers believe long distance transmission under short wavelengths was impossible, but the radio amateurs believed the otherwise, and they were right? And also another thing, interesting thing about the story was that the radio amateurs actually opened up a new form of experimentation. And in this experimentation, we can witness mass participation and networks of coordination through media and amateur societies. And this mass participated distributed experiments relied on standardized protocol and procedures for building credibilities. So thank you that concludes my talk today. Thank you very much.
Thank you so much, Chen-Pang. That was really wonderful and very inspiring.
Thank you.
Yeah, I think let's have one more round of applause for Dr. Chen-Pang Yeang.
Thank you very much. It's my great pleasure.
You're welcome. Actually, I think if I stand over, I think this is that better? Oh, how about that? Is that better? We're still getting used to this hybrid meeting thing. It's, it's really fun. If you're doing just a virtual meeting, it's easy to take care of the technology. If you're doing just a in-person meeting, it's easy to take care of the technology. When you're trying to do both, trying to make sure you're in the right places is a little more difficult. Anyway, are there any questions? Yes. So David McGaw said he knows the sunspot numbers are going to a minimum when they were doing the tests.
Yeah, so I noticed that they actually took the sunspot into consideration, although to what extent it's not very clear from the literature, but yeah, I think at that time people already had some intuitive ideas that all this had to do with the geophysical conditions of the upper atmosphere, which had to do with the conditions of the sun too. Yeah, but I mean, what was the precise relationship? They still did not have too much ideas, but I think that they already have some intuitive ideas about that.
Yeah. Yeah. Jim. Jim LaBelle from Dartmouth asks, did Appleton's discovery of the ionosphere play a role in his winning of the Nobel Prize?
Yeah. So I forgot to mention that, but Appleton won the Nobel Prize exactly for his discovery of the ionosphere. That definitely.
Yeah. So Brighton Tube, they didn't get the award. They were a year later. That was the comment.
Yeah. Oh, yeah. So not immediately, but the Nobel Prize was a tricky business, right? So sometimes people got recognitions like 40 years after they did the breakthrough work. So I don't know exactly why it didn't it didn't happen immediately, but I suppose that each Nobel Prize award winning is a complicated process of competing for nominations, etc., and the voting. So yeah, that in order to know why this happened this year or that year, probably had more to do with the dynamics of the committee.
David?
I'm sorry?
David Kazan said VE3UOT, which I presume is the University of Toronto Amateur Radio Club.
Oh, really?
Yeah. He said that he said it's a very good station and he is encouraging you to join and get your amateur radio license.
Oh, okay, okay, that's a good idea. Okay, I will touch base with them. Yeah, I think that's a good idea. We're in the same university, so that's very convenient.
Yeah. So we're all encouraging you to really jump in and join us.
Oh, okay, okay. Yeah, I'll try my best. I think it's enticing.
Yes. Kung, do we have any questions from Zoom? They said that there was a comment on Zoom that all the male PIs of the HamSCI type projects have big bushy mustaches, except for me, I guess, right? So I guess I need to get a big bushy mustache. Okay.
Yeah. Well, there's a interesting story about masculinity among ham radio, or the sort of gender imbalance among early ham radio community. So yeah, some historians wrote about that. But anyway, so
yeah, well, we're trying to be as equal opportunity as we can around here. So we're doing our best.
Yeah, totally understand.
But let's see, Jimmy Rader. So Jimmy said, none of this would have been possible without the amplifier tube. Who developed the amplifier tube?
The amplifier tube, well, it was sort of a story of multiple inventions at the same time. So Edwin Armstrong, of course, was the one of major American inventor for the developments of the feedback amplifier using electronic tube. But Meissner in Germany and Fleming, I believe he had some roles for the developments in the UK. So that was a story of independent inventions in the UK and US and Germany all around the 1910s. So yeah, so historian Sung-Gu Hong wrote a book called Wireless, which document that history in pretty good, rich detail. So if you're interested, I recommend that you take a look at that story and take a look at that book.
David, were you able to hear that, Chen-Pang?
No, actually, I can't hear anything.
All right, I'll have to make sure. That's going to be a little bit more than I can repeat, unfortunately.
Okay.
The main gist of it was Lee DeForest. The room seems to think that Lee DeForest should get most of the credit for the amplifier tube. And then they...
Yeah, well, if you're talking about the tube, right? So the tube itself, the audience, Lee DeForest was the one who invented, who claimed to invent the sort of three electrodes audience, and Lee, but James Ambrose Fleming in the UK claimed to come up with the tube earlier than Lee DeForest, but his one was a valve, which is the dia tube. But if you're talking about the feedback amplifier, not just the tube itself, but also the sort of amplifier circuit to make the sort of signal more stable, then that would wait until the 1910s, right? So Lee DeForest and Ambrose Fleming's inventions came around 1905, 06, but the feedback amplifier circuits to control the oscillations, unwanted oscillations, that came in the 1910s.
Yeah, David Kazan said the Fleming valve was used on the backup receiver of the Titanic.
Yeah, okay.
We have some radio history enthusiasts in the room here.
Yeah. I'm totally understandable. Yeah.
Yeah. Anything else? Kung? Someone on Zoom asks, what is the name of the book detailing the development of the vacuum tube?
Oh, it's called, let me write it down. It's, so the author's name is Sung-Guk Hong, Hong, and the name of the book is, title of the book is Wireless.
And Sung-Guk Hong is the author, and the title of the book is Wireless.
Published by MIT Press.
Sounds good. Any more questions? I have a question.
Yeah, sure, please.
So, what is the amateur radio community going to discover next?
That question is for you, right? So for you guys, your community. Yeah.
So that's what we're working on.
Yeah. So in this story, I emphasize I focus on the scientific discovery, right? So, but there's an equally fascinating, engineering or technological story, or multiple technological story to be told from the perspective of radio amateurs. So like radio broadcasting, that is better known by a number of historians, but the personal computers, I think that still needs some like historical studies. Yeah, so in my view, the ham radio community is the perfect, not only citizen science community, but also sort of network of grassroots technological innovation. So maybe they can come up with some like new technologies which can make some technological breakthrough of the next decades. Yeah,
I think some of the people in this room have had some profound influences on some technologies already. So
really,
yeah,
that's great.
Yeah. Let's see. Anything else? I think Bill Engelke, did you have your hand up? So the question is there a historical consensus on which frequency Marconi was using for his first, was it transatlantic experiment?
Well, so I would say that I have to check, but I would say the range of frequencies okay, put it in this way. So Marconi's I think Marconi's utilized his commercial station in Purdue, England, right? So for signal transmission. So that was not that experimental because that station was already in commercial operation. So it should not be difficult to figure out what kind of a range of frequencies that station used, even though I don't have that number in my head at the moment, but I think we should be able to find it out. So yeah, because what he was doing was not, his transmitter was not a sort of experimental transmitter. So it should be yeah, the information should be available. And I would say, yeah, given that the towers of the station was like the antenna towers like probably 10 meters or so. So yeah, it's probably kind of much lower frequencies than we thought. Yeah, definitely lower than the megahertz range. So
Yeah, the
probably like
number in the room.
kilohertz,
Yeah, the
10
number
or
in the room that
100
was
hertz.
suggested was maybe 800 kilohertz. Did you say?
800 kilohertz sounds reasonable to me. Yeah. So like 200 meters is like 1.5 megahertz, right? So yeah, Marconi's wavelength is definitely longer than 200 meters. Yeah, so.
Yeah. And Bill, did you still have a question? Sure. We have someone coming up to talk to you in person.
Oh, really? Quite great.
Yes.
Okay, thanks. Over here? Oh, okay.
Would you
Pang.
come here so that I can see you?
Yeah, okay, I'm here. We have had a lot of presentations with people
Okay.
who have been analyzing spot data. You know what I'm talking about? Oh man,
Yeah.
we've got terabytes of it. And I
Okay.
have a feeling that there is new science to be discovered in
Okay.
this data. Talk a little bit about how we go about dealing with the new things that we're going to find in this data. Because I've seen some things in some of the data that I've analyzed that hasn't yet been explained. And maybe it doesn't necessarily correspond with our current understanding of what goes on. And talk a little bit about that, because I know you know the historical perspective. So interested in your thoughts about that.
Okay. Bill, I think that's an excellent question, or that's an excellent, well, if not question, observation. I think that's precisely one important values of this mass participated science, right? So which we now call citizen science. Because for a phenomenon like the sunspots, it is complicated. It cannot be sort of reduced into simple form of representations, and to know fully about this phenomenon, we need a lot of data from different angles, from different conditions. So I think that's exactly why the community like HamSCI or ham radio community at large is valuable to the scientific research sunspot number or conditions of the ionosphere, because you guys can collect way more amounts of data that the laboratory scientists could have the resource to, right? So and also maybe not all the novel phenomena were under the spotlight for for scientific research group for one reason or another, because they have their own research program, they have their own problematic to focus on, but they may ignore new things in this front or that front. So I think the citizen science, like the amateur ham radio communities, could form an excellent complement of the professional academic science, right? So because you guys can complement, you guys can provide richer data, and you guys can actually offer different perspectives. Like the story of the discovery of ionosphere is exactly that the ham radios community were not deterred by the impossibility imposed by the current science and wanted to go further, and then they were successful. So that was a success story, but I don't mean to say that is a model for every aspects of citizen science, but I would say that's probably have some important heuristic values for us to think about the potential citizen science. So definitely, I totally agree with you about the values of this kind of endeavors.
Thank you very much. I think let's give Dr. Chen-Pang Yeang one more round of applause.
Thank you very much for everyone.
And here I have to share my screen over here for a second. Let me see if I can move it. I'm going to share this and come on, I hit share. And then I hit this over here and I hit present. So the certificate will be in the mail along with, I'm going to borrow this for a second. Oh, thank you. Yes, you'll get a certificate and you'll get a very handsome, can you see this?
I can see that.
Yes.
Thank you.
Okay. And so, yes, and you'll get a very handsome HamSCI Scranton coffee mug too.
Oh,
so
wow. Okay.
We will be in
That's
touch
cool.
and we will get that to you. Yeah.
Thank you very much. Well, actually, it would be great if you can email me a scanned copy of that certificate. That would be also handy too.
I will, and
I'll
even make sure it has the correct year on it too.
Okay.